Hello, students. 9.7 is two definitions. We have curl and divergence. We will define these two terms, and then we will see how are they used in the future sections. So today is just an introduction to those things. We will actually define those two, and we will find something called a field. So we'll start our topic with the vector functions and vector field. Remember R of t, any curve in two-dimensional space, any curve in two-dimensional space can be parameterized as what? As a vector function, isn't it? So this is what we call a vector function in two-dimensional space. This is a vector function in what? In three-dimensional space. This is how, and this is actually represents a curve in two-dimensional space, and this is represents what? Surface in three-dimensional space. So this is something that we already talked about. Now, notice here that this vector function is dependent on one variable, which is t. Always, it's a function of t. Everything is a function of t. Same thing in three-dimensional space. Everything is a function of t, which is like time. Today, we're going to introduce a different variable. Instead of being t, let's suppose that we are changing t to two variables, x and y. So this is like r of x and y, but I'm not going to call it r of x and y anymore because I need to distinguish it from the new name, guys. R is a vector function. Now we're going to talk about f, which is field. So what if I changed t to two variables, x and y? So what's going to happen? It's going to be, I'm going to change f to p of x and y. P is a function, by the way, of x and y, and g is a function of x and y. When I do this, this is called a two-dimensional, not vector anymore, vector only vector function. It's a vector field. And this is also three-dimensional vector field in three-dimensional space. So if I change t with x, y, and z, so I'm going to have p of x, y, z, I, q, r, j, and r, z. This is again a field in three-dimensional space. This is a field in two-dimensional space. What are the fields? An example of fields are like follows. As an example, guys, the motion of fluid or wind can be described by a velocity field because at each point of the fluid, we can assign a vector representing the velocity of the particle at that point. So here is, for example, the river. All those waves are representing the stream. This is stream. If you take any point here, I know that there is a vector here. Take any point here, there is a vector here. Wherever you take, there is always a vector. This is called the velocity vector. So this field of wave of water that is moving is called what? A field. Okay? Velocity field of a stream. Also the wind. The wind always blowing. You see it on TV when they show this. Then we'll talk about the speed of the winds and the temperature. They show like these things going like that. The wind is going to go this way. So at each point here, we have a vector. The set of all those vectors is a field. Field of what? Of wind. And winds have speed. So this is a velocity field. Also, the magnetism field. Remember when we were kids, we used to have like a paper, and then we'd throw this powder, metal powder on it, and underneath we have a magnet, and then we shake it or we hit it a bit. What do we get? We get that field. I think you remember that graph that we have those kinds of fields, right? The magnetic field, you get something like this. So this is what we call the magnetic field. Okay, so magnetic fields are also another example of what we have here. You know, if you're standing on if you are somewhere in standing water, standstill water, and you throw a rock in it, what's going to happen? You will establish what? A field of waves, isn't it? So this is a field of waves, right? So there are many waves, many kinds of fields. Also the force is another kind of field, the force field, okay? And force field will actually move things. So this is exactly what we're going to discuss in this remaining sections of this chapter. We will focus now, and instead of really focusing on the vector function. Now we're going to focus on vector fields. All right, let's look at any two-dimensional vector field, guys. Let's take number A. Let's see how the graph looks like and what kind of field is that. All right, so now we have f of xy is equal xi plus yj. Now, what's the magnitude of this vector field? I'm going to measure the length of each what? Each vector in the field. Remember, what's the magnitude of that? It's the square root of the first one square plus the second one square. So the magnitude of any vector in this field is this one, right? So we have, remember, field is what? An infinite number of vectors. So I'm going to take the magnitude of this field, of every vector in the field. Let's get it. So we get this one. Let's suppose that this is equal to k, guys. So what do we have now? We have x squared plus y squared is equal to k. Square both sides, by the way. So what do we have now? We have x squared plus y squared is equal to what? K squared. What is this? This is an equation of radius k, isn't it? So this equation of a circle of radius k. So this is circle of radius k. All right, now let's take k 1, guys. So what do we have? We have x squared plus y squared equal to what? 1 square, which is 1. And this is a circle of radius 1, right? All right, how does the graph look like, guys? So I'm going to make the graph now. Let's take the black one for the axis. Here is our axis, the y-axis, and the x-axis. All right, now we have a unit circle, circle of radius 1. So let's suppose this is 1. This is a 1. This is -1. And this one is -1. So what I'm going to do, I'm going to graph the circle. The red circle here, here it is. And then probably we can go down here and then go up there. So this is a unit circle, guys. What's this point here? This is 1 and 0. This one is x0, y1. This is -1 and 0. And this is 0 and -1. So I have those 4 points on the circle. Wonderful. Now, what I'm going to do, guys, I'm going to find the value of the function at this point here, at this point. What's f of 1 and 0? What's f of 1 and 0? So I'm going to replace x with 1. So we get 1i plus 0 what? J. And I'm going to write this one as an order pair. So it's 1 and 0. Where is 1 and 0, by the way? Isn't this of the vector 1 and 0? This is our vector 1 and 0. This is f of 1, 0. It's this vector. But I need this vector not to start from the origin. It has to start from where? From that point that I took on the circle. So this one is going to move here, guys. So this one actually is f of 1 and 0, not this one. So I will not need that one. Okay. And this is now our vector. Now, let's take f of the other point, which is, for example, what? 0 and 1. F of 0 and 1 is definitely 0i plus 1j, which is 0 and 1. Where is 0 and 1? It's going to be this one, right? This is 0. This is the curve. The vector 0 starts from the origin, ends at 0, 1. But I don't want it to be here. I want it to start from here. So this is f of 0, 1. So this one is going to go up there. Alrighty, so I'm gonna remove this. I don't want this green one. I will take the upper one. Similarly, f of 0, sorry, -1 and 0 is going to be definitely -1 and 0, and is going to be this one, by the way. And the last one, f of 0 and -1 is going to give me 0 and -1. I know that 0, -1 is this one inside, but I'm going to put it out on what? On that point, at that point. So everything is at the selected point. So what's happening here, guys? The field is going to push this circle outwards. And actually, I did all of this only for what? For k equal to 1. What if I change everything, and now let's take k equal to 2. What's going to happen? We have x squared plus y squared equal to 4, right? We're going to plug it here. So this is a circle of radius what? 2. So I'm going to make this next circle of radius 2. Now this is a circle of radius 2. What I'm going to do now, I'm going to extend my axis. X-axis and y-axis goes this way. And it goes all the way down that way. And it goes up this way. Now, what I'm going to do, I'm going to find now f of, what is this point, by the way? This point is 2 and 0, isn't it, on this circle? And this point here is 0 and 2. This point here is -2 and 0. And this point here is going to be 0 and -2. We will apply the same thing. What's f of 2 and 0? Definitely, this is 2i plus 0j, which is 2 and 0. Where is 2 and 0? It's the vector that starts from here, by the way, and goes all the way there, but I'm not going to take this one. I'm going to go this way. So the second one, f of 0 and 2, it's going to be 0 and 2. 0 or 2, this vector that starts from here and end up here, but I'm going to shift it and move it down up there. So I'm going to take this one in different color. So let's take the blue one now. So you know, we have one coming this way. We have another one coming up. We will have another one coming this way. And from here, we have the one that goes that way. So the next circle, another force is going to push it out. So what's going to happen? All those are construct what's called what? A wave field, isn't it? So we have here a wave field. So this one represents a wave field. Circle pushed outwards. The next circle pushed out. So there's something is pushing it out. So what do we end up with? A wave field. Let's look at the second one, guys. Part B now. We have f of x and y is minus yi plus xj. All right, what do? We take the magnitude of f. It's a square root. If I square the first part, I get y squared. If I square the second one, what do we get? X squared. Let's call this one again what? K. Square both sides. So we have x squared plus y squared is again what? Circle of radius k. Let's take k to be 1. So what do we get? We get x squared plus y squared equal 1. Circle of radius 1. So I'm going to graph now the circle of radius 1. Here is 1, 1, -1, and -1. So now I will graph this one in red. That's our first circle. So this point is 1 and 0. This one is 0 and 1. This one is -1 and 0. This one here. Those are our points. And this one is 0 and -1. Alrighty. Now, let's find the field at the point here, 1 and 0. All right, what's f of 1 of 0? Be careful now. The formula says minus y, so it's minus 0i plus x is 1, so 1j, and this is 0 and 1. By the way, where is 0 and 1? 0 and 1 is this vector, right? This is our 0 and 1. So I'm going to change the color, make it blue now. This is the vector 0 and 1. But it shouldn't be here. I have to graph it here on this point. So here is our first vector. So what kind of force here? There will be a force that is going to push this point 1, 0 up. Okay, let's see what happens at this point, guys. F of 0 and 1. So this is x, by the way, and this is y. So this is minus 1i plus 0j, and this is minus 1, 0. -1, 0, this is -1, so it's supposed to go this way, but I'm carry it and put it there. So this is the second wave. F of -1 and 0. What is this? This is x -1, y is 0, so this is 0, I minus 1j. So it's 0 and -1. Where is 0, -1? We know this is the vector 0, -1. But I don't want it to start from the origin. I want it to start from here. So this is the third vector. So what's going to happen for the last one? F of 0 and -1 is going to be I plus 0j, right? Because x is 0, comes at the end, and y is -1, and there's already minus, so it's 1, and this is 1 and 0. Where is 1 and 0? This one is 1 and 0. So at this point, I'm going to make a vector that goes this way. So what's happening here, guys? There is a force that's going to what do to the circle? It's going to rotate the circle. And the same thing is going to happen for the next circle. So let's go to the next circle if you like. Here is a circle of radius 2. If I take k to be 2, this is when k is equal to. So this point is 2 and 0. And this one, 0 and 2. This one is -2 and 0, and this one is 0 and -2. Now, what's going to happen in the next circle? Same scenario. Here, you will go all the way up. Here, you will go to the left. Here, the same thing is going to go down. And from here, you're going to go to the right. So what's going to happen? A force is going to come and rotate the next one. So what kind of field is this? I think this is what we call a whirlpool, right? Rotation. And this is what the ships try always to avoid on the ocean when they go to the ocean. So now we have a field of what? Of whirlpools. Make sense? So this is a rotation field. Rotation field, and this rotation field is called what? It's called a whirlpool. And it's rotating counterclockwise. Right? It's a rotating field counterclockwise. Exactly what I have. And this is, in one word, this is called a whirlpool. There. This is how the graph looks like neatly by using the software. All right, now we're going to go and define another thing called the del operator. Let's suppose that f is a function of 3 variables, guys, x, y, z. It's a scalar function, not a field. It's just a scalar function. Do you know what's the gradient of f? Remember, it's the partial derivative with respect to f, with respect to x, then y, and z. And this can be written like that, df over dx, df over dy, and df over dz. So the gradient is a vector. Now, I will take the del operator to be only the derivatives, guys, without f, without putting f, just the operator. Okay, so the del operator is going to be exactly the partial derivative with respect to xi, partial derivative with respect to y, partial derivative with respect to z of what? You're free to put whatever f you like here, any scalar function there. Where any function of x, y, and z can be put there, and this will be the del operator. Now, let's suppose now I have a vector field, guys, in three-dimensional space. I'm going to define what's called the curl FF. What's the curl of f? The curl of f is exactly the determinant of ijk. Then this one is what, guys? The middle part, all of this is the del operator. The last one are the components P, Q, and what? And R. So this is the field itself, huh? So I put the components of the field. And remember, this determinant represents what? Isn't it the cross product between the del operator and the field? All of this, guys, is the del operator. And this one, the components of what? Of the field. Those are the components of the del operator plus the components of the field. And this is going to give me what? Something called the curl of f. We'll define later on what does it represent in real life thing. Also, if f is a vector field in three-dimensional space, then we're going to define something called the divergence of f. What's the divergence of the field? It's the partial derivative of the first component plus with respect to x, the second one with respect to y, and the third one with respect to z. And if you look carefully, this is the del operator dot f, isn't it? This is the del operator, by the way. And this is our field. I put it as a vector. You know the dot product. What's the dot product? This times that. So it's going to be the partial derivative of this with respect to x, the partial derivative of this with respect to y, plus the partial derivative of this one with respect to y. So it's a dot product between the del operator and the field. The del operator, the divergence of f, actually represents the flux of fluid from a tank. When the water comes out of the tank, this is what we call, when you open the faucet and the water comes out, this is called the flux. We can measure the flux by something called the divergence of the field. So the divergence of the field is the flux. What's the curl of the field? I have no idea so far. We will talk about it in the next section. But now let's just take example of how do we compute the divergence and the curl. Let's start, guys, with the curl of f. What's the curl of f equal to? We put like this, I, j, and k. And what do we put here? The del operator components. And down here, what do we put? P, Q, and S. So this is P, 3, x squared y. This is Q, 2, x z cube. And this is R, which is y to the 4. Do you remember how do we do the determinant? We showed you before. We take the first two columns and we put them out. And then the j. And the last one, 2xz cube. All right, now what do? We go diagonally like that. So this is equal to. Okay, let's start. The derivative, so it's d over dy of what? Of y to the 4. This is what you get here. All of this is what? All of this I. Plus. Now what? Go this way. It's d over dz of what? Of 3x squared y. J. Plus the partial derivative with respect to x of what now? Of 3 of 2xz cube. Then what do we say? Minus. We go backwards now. It's d over dy of 3x squared y. This is k, right? Backwards, it's a k. By the way, we forgot the k here. Minus this way now. So it's d over dz of 2xz cube, 2xz cube. And this is, by the way, if you look here, this is I, and minus, with the j, we have d over dx of y to the 4, all what j. This is how you find the determinant. Now, what's the derivative of y to the 4 with respect to y, guys? We know this is 4y cube I. Now, what's the derivative of all of this with respect to z? You know, when you differentiate with respect to z, x and y are constants. So what do we get? We get 0j. What's the derivative of this partially with respect to x? We only differentiate the x. What's the derivative of x? 1. So what's left is what? Plus 2z cube k. Now minus. What's the derivative of this with respect to y, guys? The derivative of y is 1. Everything is constant. So this is a 3x squared k. Minus. What's the derivative of this with respect to z? We only differentiate z cube, which is a 3z squared, and there is 2. So 6xz squared I. How about this one? What's the derivative of y to the 4 with respect to x? There is no x to differentiate, so y is constant. So this is minus 0j. So what do we end up with, guys? What we have is, let's look at the I. Here is the I. And where is the other I? This is the other I. So we have 4y cube minus 6xz squared I. Then j, there is nothing, plus 0j. Both of them cancel, but don't leave it, write it down. Then finally, what do we have? Plus, we have 2z cube minus 3x squared k. Now this one goes away, and we have 4y cube minus 6xz squared I plus 3z cube, or 2z cube minus 3x squared k. This is the curl of f. Now let's compute the divergence, guys. What's the div of f? The div of f is the partial derivative with respect to x of what? Of p. This is p of a 3x squared y plus the partial derivative with respect to y of q, which is 2xz cube j, plus the partial derivative with respect to z of the last one, which is y to the 4. And this is, sorry, there is no j or k. My apology here. So there is no j here, and that's it. So it's just a scalar, which is equal to, what's the derivative of this one with respect to x, by the way? With respect to x, the derivative of x squared is 2x, and there is a 3. So this is 6x, and we don't touch the y. What's the derivative of this guy with respect to y? Nothing. There is no y, so 0. Plus, what's the derivative of y to the 4 with respect to z? There is no z at all, so constant, 0. So the final answer is 6xy. This is the divergence of f. All right, so this is 2 definitions, curl and divergence. This is how we compute them. And then we talked about the fields and how you define the fields, and the del operator. We need the del operator, the graph of the field, and understand what's a vector field. The del operator, the curl and the f, and the divergence of f is what we discovered and we covered today in this section. All right, and that actually concludes everything in this section. So there isn't much actually to cover. We're going to take those 2 definitions, all definitions, in the next part. So you need to, when I say curl and divergence, you have to understand how do we compute those. And later on, you will understand the meaning of those. You guys have a good day.